Hello again. So today we have another HP meter from the Yokogawa group in Japan. This is the HP4329A high resistance meter, and this is somewhat like a megger in the sense that it actually puts out very high voltages to measure resistance, and it uses a completely different principle compared to normal resistance meters. Either low or high resistance, does not use choppers or other kinds of circuits to remove offsets and drifts and so on. This uses a completely different approach and what they call a parametric converter. I'll go into the details of that, but essentially it consists of another bridge here in the input stage, which converts an input current from an unknown resistor, and the current is then converted to an AC signal, which is then amplified and then converted back to DC to display on a meter. There's also some feedback involved over here to balance the bridge, in the sense that it actually creates oscillations, but the principle is quite interesting, and I can go in discuss that a little bit in detail. And what I've shown here at the bottom is the principle of operation for this particular input circuit, which involves a pico diode, actually a pair of them. I'll have to describe what that is in a later slide, but that pico diode is not essentially used as a diode but mostly as a capacitor, variable capacitor, and based on its bias voltage, its capacitance changes, as you can see over here. As you increase the bias, its capacitance increases, and as you decrease the bias negatively, it decreases. So using that principle, it creates an imbalance in the bridge, and then that signal is then converted to an AC signal, which is then, as I mentioned, amplified and converted to DC, eventually to displayed as a resistance indication. So this is a diode characteristic, as you can see here. This is a breakdown, the reverse bias, and then this is a forward bias. But the actual, since you're only interested in the capacitance of this particular thing, you're operating in the more or less cutoff region here, in between the positive and the negative parts of the diode, where it takes off, the voltage, the current takes off. And when you operate in this region, you get a linear capacitance based on bias. And the nominal capacitance for this when it's biased at 0 is around 100 picofarad for this particular diode, and capacitance curve is, as you can see, it's a slightly linear curve across this small operating window over here. Okay, so let's look at this the bridge configuration that is key to the operation of this instrument. We have these four devices, C1, C2, the two pico diodes, and they have extremely low leakage in the operating region where we're talking about, where they are not forward biased or in breakdown. And it's an order of tens of picoamps, I guess. That's what I read in the specs for these diodes. And you have two R's which are equal, and you have this CT capacitor, which is around 20 picofarad, whereas these two, C1 and C2, at 0 volts would be 100 picofarad if they are both have the same voltage across them. Now, in order to maintain the bridge balance, you have to have all these two arms equal and these two arms equal. So what happens is that C2 must be less than C1 in order to balance the bridge. So if you look at that, then you see that you have to have this go down to 90 picofarad and C1 go to 110 picofarad. That puts voltage across this bridge, which is then provided by the amplifier. So the amplifier really powers this bridge and also maintains the balance through negative feedback. So let's assume if we change CT now, if you increase CT slightly, this capacitance overall increases, and because of the division principle of capacitors, you have this voltage decreasing across this cap here, these two parallel caps, and that then causes the bridge to go out of balance, and then this amplifier tries to correct that. And the speed at which this corrects this is really the key to this operation of this circuit, that creates an oscillation because it's slow enough that it does not compensate it instantly, but it takes some time, which then sets up overshoot and instability, basically like in a negative feedback amplifier with low phase margin in that sense. So it sets up an oscillation which is in the hundreds of, I think 100 kilohertz roughly. And that amplified signal is then amplified through the amplifier chain, which then goes to which is then rectified and then displayed on the meter. So in order to convert this to a resistance meter, what you need to do is to inject another current which is further imbalances the bridge. So assuming that at this point CT is held at some balanced value, now if you put in an IX current which is proportional to an external resistance that you're trying to measure, then that will also cause this bridge to get imbalanced, and that same thing will cause an oscillation which then can be amplified and then displayed as a effective resistance in the meter. So the combination of imbalancing either through the capacitor or current coming in from through an external resistor, high resistance which is in the picoamp region, or very very small amount of current, can significantly imbalance this bridge that causes this oscillation, which then is used as a parametric converter. And the parametric thing that you're really using is the capacitance of these diodes. That's why it's called this parametric converter, and that principle is really unique in this particular instrument, and I guess in future instruments that were based on this principle. So now we look at a little bit more detail the entire instrument in a simplified block schematic with some critical components shown here. So on the left side we have the parametric converter as we described earlier, and then we have the AC amplifier for the meter, and then the output stage which has a rectifier and the meter output. And there's also some feedback which I will talk about over here on the top. So looking at the meter itself, you have the resistance connected between the center point of this input to ground, and you have a 56 megohm resistor in series with the two picodiodes over here, CR1 and CR2. CT is the capacitor we talked about that tunes the bridge to create a certain voltage when it's balanced, and that the DC current that's basically created by the resistor connected over here is then sent into this diode over here, and it causes the mismatch in this particular circuit over here, which is then sensed by this the oscillations which are created by this feedback loop within this parametric converter is then using a series resonance circuit is amplified and then fed back M3 back to M2 M1, which tries to rebalance the bridge, and that is the one that sets up this entire oscillation over here, and this is tuned to around 100 kilohertz roughly. And the output of that is also then coupled into the secondary stage, which is the AC amplifier, which then it goes through a set of full wave rectification over here, and then that output is then fed into a meter with certain time constants to make sure it doesn't it's stable. And there's also a recorder output that goes, which can be used to drive a XY recorder if needed. There's a feedback loop over here, which is here shown with this 10 meg 20 puff, which goes to the center tap of this resistor, which is used to compensate for some for the characteristic of the picodiode. This is not part of the main oscillation loop, of course. It's just a DC feedback loop. And then there is another feedback loop which is used to cancel out any leakage currents that may exist, because when you have a high voltage on this on the resistor that is being measured, you could have leakage from that resistor into its outer to ground basically, or to the cable itself, which then will distort the measurement. So in order to prevent that from happening, they maintain the guard voltage around that cable at the same potential as the measurement. So any leakage is basically cut off into ground. So that's the important part of this particular instrument in trying to measure extremely high resistances. So I believe this instrument can measure something like 10 to the 15 or 10 to the 16 ohms, which is extremely high. And of course you would need to be for those type of values you would have to apply a 1 kilovolts DC level. Can also measure at lower voltages, but then your maximum resistance that can be measured is lower. So this is a fairly versatile instrument that can measure from a few mega ohms to hundreds of tera ohms or even beyond. Now the practical use of this instrument, of course, is unless you have the right probes and the right technique to measure such high resistances, you're probably going to get incorrect results if you don't do it correctly. You need to have extremely good cables and the shielding and so on. I don't have the correct cable for this one, but I'm really going to be measuring above 10 to the 12 at the most, my limited use of this instrument, but it can of course measure several orders higher than that, so it's definitely capable of that, like a real mega instrument. There's also an option to measure current, and of course that comes from naturally because you're essentially measuring a current over here, and you can actually display the meter also in terms of current or resistance, whichever you like. So here's the HP4329A. I basically bought it as a scrap. I wasn't sure if it was working. I thought I would take a look at it and see if I could fix it. The reason I got it cheap was it lacks the original template display which shows the resistance readings that are being selected, and also the currents over here on the right side. As you can see, I'll switch to the ranges to show you. So the minimum it can go is 10 to the 6 ohms full scale, 10 to 7, 8, 9, 10, 11, 12, 13, 14 and 10 to the power 15. And if you go to the higher ranges, you'll see the 10 to the power 15 will actually light up. It's higher voltage settings, test voltage settings. Similarly, if you switch the current, you'll be able to get to see the current scales, and that's the highest minimum current, which is 1/10 of a picoamp, and you can basically again go to the highest current, which is a microamp reading. So the way it works is you first charge the device and then you do a measure. So it's basically sets the DC level, and then it once, if you're measuring a capacitor, for example, you may want to first charge it to get rid of all the initial charging current, and then you can do a leakage test on the capacitor, for example. So anyway, this is right now set at 10 volts, and I'm going to measure a 32.1 mega ohm resistor. This is the highest value that I have with me right now, which I measure on a different meter, and that meter is capable of measuring up to hundreds of mega ohms. But this one will have no problem with such a low value resistor. So you can see on the left side over here the scales that are being indicated. You can see it switches to the different scales depending on the voltage that you set. So there are 3 or 4 scales over here. So I'm going to just measure it at 25 volts. This is going to be 32 mega ohms, so this is 100 mega ohms full scale. So resistors don't require to be charged up, so we can immediately go to measure. As you can see, it's actually reading 31 mega ohms, which is pretty okay, I guess, for this range. Let's see if I can get it at a different voltage. So on a 50 volt test, I'm seeing again 31 mega ohms, same value. On the 100, it's also reading around, yeah, it's basically not enough resolution on this scale, but it's around 30 something, little over 30, 31, 32 mega ohms again. So it's pretty useful. I think if you want to measure into the hundreds of mega ohms and giga ohms and above, I think this meter will have no problem doing it. Of course, you got to be careful when you're operating anywhere above 100 volts that you shield yourself, don't touch the terminals while it's being measured. You do need a good cable here with the outer guard and everything, which I don't have, and those cables tend to be more expensive than the instruments themselves these days. The way it works is in terms of polarity, the resistance, the positive voltage is applied on this node for resistance measurements, and the center conductor of this BNC is actually the negative return current, node for the resistor. For current measurement, the positive current comes out of this center, and then basically the negative is on this particular terminal over here, so it's reversed. Besides that, there's a current setting, as I mentioned. There's a guard, of course, if you want to apply a guard to the cable measurement, and if you're really measuring the teraohms and gigaohms, you would probably have to try using that guard to make sure you don't pick up unnecessary leakage. So this basically concludes the demo and brief description of the instrument. I forgot to mention one thing. When I got it, it was basically working, but the scale, when I was switching through the different test voltage ranges as well as the actual range, I was getting a lot of noise, and it wasn't very, the output didn't make sense. In fact, it wasn't even working properly. So then I cleaned all the contacts, internal contacts on the switches for both of them, and that brought it back to life. The other thing I found was when I went into the 500 or 1000 volt range, there was a kind of a buzz that was coming out of the instrument, and then when I opened it up, I found that one of the wires that was connecting into a shielded area of the instrument was arcing. So that was actually making that buzzing sound, and also the voltage, the reading was fluctuating heavily because of that poor connection, or not connection, basically the leakage from the voltage itself, the test voltage that was going into the test device. So I cleaned that up, put a proper insulation, and re-wired that, and now it's absolutely working perfectly over all the ranges now. So thanks for watching. See you next time. Bye.